So we're starting with the definitions of a mixture. We've already introduced the terms, but we'll have them listed here from slide 36 on. So binary mixture, that's what we're talking about. We need to be able to quantify the number of particles or moles per unit volume, and that's what we call the molar concentration. Written with a capital C, the units are kilomole per meter cube, and essentially it represents the number of moles of a species, it could be A or B or C and so on, per unit volume of the mixture, not of the species, of the mixture, but essentially the species occupies the same space as the mixture, except it's more sparse because it's distributed across a wider area, or that's a way of saying it, but essentially you use the mixture volume. We use that symbol here, the V with the bar, to distinguish the symbol from the letter V, which we use for velocity very often in this course. So capital V would be velocity, and this one would be volume. So it provides a measure of the proportion of the species I in the mixture. For example, considering the mixing of two species that are initially separated by a membrane shown here. So initially, if they're fully separated, it means the concentration can be assumed uniform and constant at that level. That is, the concentration of species A is here. So you have the same distribution throughout space along the x direction. And then when you go into the second part of the container, that is in the second compartment, the concentration of species B is shown in this particular example to be at the same level. So initially, for Ca, you've got a straight horizontal line and it drops like a cliff edge down to 0. So you've no species A in the second compartment. And it's the opposite for the concentration B. But from the minute you, or the second you open the container, that is, you remove the membrane separating the species, then you end up with a mixing. The mixing may be a combination of diffusion, pure diffusion with convection, different processes, but essentially what it means eventually is that your species B will occupy the whole volume that the mixture is taking up. Okay, so you have a distribution of the two species, dark pink and light pink. Okay, so that's the molar concentration. The mass concentration, we've already defined it as kilogram per meter cube, and the letter that we use is rho, so the Greek letter for R, and it's defined as the mass of the species I divided by the volume. So very similar to the molar concentration, where we looked at the number of species divided by volume. We're now looking at the mass of the species divided by the volume. The mass of the species is the same as the number of moles multiplied by the molar mass, where we introduced the molar mass previously. So molar mass is kilogram per kilomole, and then the number of species is kilomole. So when you multiply these two together, you just end up with kilogram. That is the mass of the species I. Both form of the concentration must satisfy this condition. That is, if you have a mixture of n species, and S stands for the number of species, you need to sum rho I from 1 to ns, and for each of the row to get the total density of the mixture. Okay, so the individual density of the individual species, when summed up, will give you the density of the mixture, and the same for the concentration. So we must satisfy this no matter what. Another useful term is the molar fraction, which is essentially the number of the species of moles of the species I compared to the total number of your mixture. So you have perhaps 10 moles of species I for 100 moles of mixture. So you have 10% of the mixture is made up of species I. That's the way you would define it. You can prove that it's the same as the ratio of concentrations, molar concentration, and also you can prove for an ideal gas that it's the same as the partial pressure of species I divided by the pressure of the mixture. The partial pressure for a mixture like this one of, let's say, species A would be the pressure that would exist in this container if you were to remove the species B. Okay, so if you remove the species B, the pressure due to the presence of the species A will be less than the pressure of the mixture, because essentially you end up with less particle in it. So that means that the molar fraction is the same as the fraction of partial pressure to total pressure of the mixture. It can be proven reasonably easily. Then we did talk about the convection diffusion, HM. I'll scroll back up to the corresponding slide. You remember that when we defined the mass flux, we used the convection mass transfer coefficient, HM, which looks very similar to the convection coefficient for heat. If we go back to our slide, we have an actual mathematical definition, which is very similar to the one used for convection heat transfer convection coefficient H. So in that case, we are going to equate essentially diffusion heat flux with convection heat flux. You remember we looked at it in the context of heat. So let's take another sketch here. Imagine that you have your surface and you've got, let's say, diffusion of your species A right there at the solid surface. And after that, you've got convection by bulk motion. This type of thing. So bulk motion of your gas will lead to convective transfer. Whereas if you've got a very organized or very close to the surface, the molecule, even if it's gas, are not going to move freely like would be the case outside of that initial layer. So it means even if you have a gas which moves everywhere, almost everywhere, in the very, very small layer near the surface, due to the surface roughness, you end up with a diffusive process. That is, you don't have bulk motion of the molecules. So it means that when you're looking at the transfer of mass through in the direction perpendicular to the surface, you will have always diffusion to start with. That is a process driven by gradients. And then you'll have everywhere here convection. If you have a steady process, the amount of mass by diffusion through the initial layer has to be equal to the amount of mass transfer by convection. If you had a difference between these two, you'd have an accumulation or a reduction in the amount of mass here. And we're talking about a steady process. Steady means things don't change with time. So you can't have an accumulation or a reduction with time. So you have to have that balance. And the way we write that balance is we use the mass transfer equation. And we say it's equal to the diffusion transfer of mass Okay, so that equation on the right-hand side looks almost exactly at Fourier's law of heat transfer by a diffusion. That is, you remember we had a coefficient of diffusion heat transfer multiplied by a gradient in the direction perpendicular to the wall. Y here refers to the direction perpendicular to the wall, and we evaluate it at the wall, so right here. That's how we can say that it's diffusion. So we have the same here. We've got a mass transfer or diffusion coefficient for mass transfer. We write it D, AB, that is for a mixture of A and B, and that's the one that you use for the diffusive transport of species A. Then you have your gradient of molar concentration in the direction perpendicular to the wall. So it's very, very similar. It's the same. And this law is called Fick's law of diffusion. We see it written here with a J letter in bold, which means that it's actually a vector. So instead of using dCA over dy here, we use the Nabla operator, which stands for the gradient of the concentration Ca. And we can prove that this here is exactly equivalent to an alternative there where we have the concentration of the mixture multiplied by the gradient of the molar fraction. So not the mass fraction. Y was the mass fraction. X is the molar fraction. That is the fraction of concentration, molar concentration Ca divided by the molar concentration of the mixture. So we can prove that these are equivalent. It's not critical. We essentially just use this one here in one dimension. That is, the gradient is assumed to be in the direction perpendicular to the wall. Otherwise, we'd have to use something like that. So here we have diffusion, and we balance it with the mass transfer equation by convection. So this equality, if you rearrange it slightly, gives you this, right? You just divide both left and right hand side by what's in the brackets here. CAS minus CA infinite is the difference in concentration, molar concentration, across the the concentration boundary layer. And that's the official, or the theoretical definition of your convection mass transfer coefficient. I'm going to address this in another recording.